Okay, hello and welcome. My name is Jose Fuentes, and today's date is November 13, 2024. This is my research presentation for my final project, and this is solving the traveling salesman problem using GA or genetic algorithms. So, the objective is this project aims to use genetic algorithms to find near optimal solutions for the traveling salesman problem. This includes designing enhancements such as heuristic initialization, and wisdom of crowds approach to improve solution quality. I choose to tackle the route inspection problem, which is also known as the Chinese postman problem. Um, okay, and why did I choose the IPS? So I initially chose the CPP because of the practical logistics of transportation and municipal services applications. It seemed like a problem that had a real world impact, such as optimizing delivery routes for garbage collection or street cleaning. Okay, so problem definition. What is TSP? So it's all about finding the shortest route to visit all cities exactly once and return to the start. It's widely applicable in logistics, route planning, and even robotics. Some challenges are it's computationally hard for larger data sets. So the larger the amount of data you're running through, it's going to take much longer to compute and you'll need more computing power. It's also difficult to optimize or make efficient. Okay, so genetic algorithm overview. What is a GA? It's a nature-inspired optimization algorithm, and some core operations are population. So in this case, set of candidates, solutions, routes, selection, picking the fittest routes for reproduction, crossover, combining parent routes to create offspring, and mutation, the random changes that happen and maintain diversity. Here we have the initialized population start, then evaluates fitness, selection, crossover, mutation, and repeat. Okay, so problem specific enhancements. Challenges in solving the CPP, Chinese postman problem, or RIP. So traversing every edge with minimal backtracking, handling non-Eulerian graphs, odd degree vertices, balancing optimization and computational cost. Some enhancements I made that I'm quite proud of, honestly. It's heuristic initialization, minimum spanning tree, and ensuring a good starting route, MST. Wisdom of crowds, WOOC, aggregates the base routes from the population, and adaptive mutation rates, which maintain diversity and avoids premature convergence. So when parsing through the input data, I also chose the same TSP files we've used in the past two projects. It was just easiest thing to do, and I was already having a hard time coming up with the proper data, so I was like, this will do. So this function reads the TSP files and extracts the city coordinates, and it ensures compatibility with a TSP style input. And I had some error handling just in case it wasn't reading the file format properly. So pre-computing distances is one of the first functions. Why pre-compute distances? So it avoids redundancy in Euclidean distance calculation during fitness evaluation. It also improves computational efficiency, period, overall. And this is the function I wrote up for it. Okay, so population initialization. Combining MST base, initialization, and random routes. MST ensures initial high quality solutions from the beginning. And it also does random routes and adds diversity. And the way it works is it builds an MST from the graph, shuffles the MST, derived nodes for variations, and adds purely random routes. And here's the function I had defined heuristic initialization population, cities, distances, and population size. Fitness function. So this is my function for calculating fitness with routes and distance as some parameters. Evaluate route quality based on the total distance, and the lower the distance, the higher the fitness. And this matters because it guides the algorithm towards a shorter, more optimal route. And like I said, high fitness for shorter distances. Okay, functions. Genetic operations. So I started with a determinant selection, and for me, the parameters were population, fitness, and tournament size. And here I have some comments within the code that I will be showing later. And select one individual from the population using tournament selection parameters, which are population list, the population of routes, fitness list, the corresponding fitness scores for each individual in the population, tournament size, int, integer, the number of individuals to include in each tournament, and then it returns a selected individual, which is the individual selected as a winner of the tournament. Okay, crossover and mutations. So my function for the crossover, I use a heuristic with edge and parent 1 and parent 2 as nodes, and this combines segments from two parent routes. And then function for mutation was smart swap mutation, the name I gave it, individuals and mutation rate. It just swaps cities to maintain diversity. And these are some comments that I added to the source code. Applies for the mutation function. Applies swap mutation to an individual's route with a given probability. Arguments individual list, the route to mutate, and mutation rate float, the probability of performing mutation. It returns a list, the mutated route, of course, and then the mutation process randomly selects two positions in the route and swaps them, introducing variation to avoid local optima. Main J function initialize the populations, evaluates fitness, applies selection, crossover, and mutation, and it tracks the best solution and fitness progress over generations. These are the default settings I chose when you run the algorithm. Population size at 50, generations at 100, and mutation rate at 0.1%. This was just simply the quickest, but I'll show you in a second that you're able to input uh, whatever you choose to put. I'll show you. Experimental setup and results. So in tackling the mixed graph route inspection problem, I compare the following metrics across the standard GA and GA with WOC approaches. So solution quality cost, minimum, maximum, and average path length achieved, conversion rates, the rates of improvement over generations, runtime performance, and the total runtime and average runtime per generation. So here are my metrics, minimum and maximum path length, average path length, standard deviation, and average runtime. Before adding the WOC and heuristic approaches, the algorithm was taking around 2 minutes and 15 seconds to run to give me the output once I executed it. And then after I added the WOC and heuristic approaches, it dropped all the way down to 5 seconds, which even less than 5 seconds was quite nice. This was the best route that I got with the default settings given 50% population, 100 generations, and a 0.1 mutation rate. And then the fitness progress graphs illustrates a faster convergence rate for the GA and WC approach, stabilizing solution quality in fewer generations than the standard GA. The WC guiding effect on convergence was especially noticeable in the initial generations, where the consensus route helped the algorithm avoid low quality solutions. And once again, the population size is default to 50, generations at 100, and mutation rate at 0.1. And you can see a nice, fine fitness curve from 0 generations all the way up to 100. Discussion and analysis. So the GA and the WC approach for the mixed route inspection problem showed significant benefits over the standard GA. It improved convergence. The consensus route reintroduction allowed the GA to reach high quality solutions faster. Solution stability. The GA plus the WC method produce solutions with lower variance in path length, suggesting more consistent outcomes. Handling of mixed edges. The custom crossover mutation functions effectively preserve the edge orientation, ensuring compliance with mixed graph transversal requirements. And some challenges was a flat progress in fitness for some configurations, depending on the percentage rates for mutation you put in, and increased runtime for larger cities. So if you go over 500 generations or over 100 population size, the runtime increases dramatically. Limitations and future work. So computationally expensive for large graphs, like I was talking about. The larger the population or mutation rate, you'll get a much longer runtime. So it depends on initial parameters. And then future work, fitness evaluations, testing on larger data sets, exploring alternative crossover techniques. Some improvements I could make is adaptive expert selection. Experimenting with adaptive expert selection could refine the balance between exploration and exploitation. Enhance heuristic initialization. Investigating heuristic initialization methods, considering both directed and undirected edges, could improve starting population quality. My conclusion was in this project, I successfully applied a hybrid GA and a WOC approach to the mixed graph variant of the route inspection problem, also known as the Chinese postman problem. The results show that incorporating a WOC and a heuristic initialization can yield a high quality, stable solution for more efficient than standard GA. This approach highlights the potential of using collective intelligence in evolutionary algorithms to address complex routing problems, specifically in mixed graph scenarios. And future work could improve exploring alternative aggregation methods and testing the approach on other mixed graph problems. Alright, so this is my code for my final project, and I'm going to go briefly over some of the details that I had written up for the code. So first step is parsing the TSP file using the parse TSP file function. This extracts the city coordinates and stores them for later use. Here are some of my functions. I'm trying to get to heuristic. Okay, so the heuristic initialization population creates the initial population, and halves the route are derived from the MST, minimum spanning tree, ensuring a high quality starting routes, while the rest are randomly generated to maintain diversity. This combination of heuristic and random routes gives the algorithm a good balance between exploration and exploitation, as I have mentioned in the PowerPoint on some slides. And let me get to my main algorithm here. Okay, so here. Um, so the main algorithm, genetic algorithm, CPP, evolves the population through selection, crossover, and mutation. Fitness is evaluated using the calculate fitness, which is right here. And the fittest individuals are selected using the tournament selection, which is right here with this function. And over multiple generations, the algorithm tracks the best solution and fitness progress. Here, I'm gonna run it real quick for you guys. It'll default setting their 50 population size. Generations are at 100 and 0.1% for, but you're able to input whatever, let's say 10%. for mutation rate. I added this progress bar because I thought it was kind of cool to do. And then these are the results. And then if I want to get the best route, I'll just print that. Let's run it again. Here, default settings, and then I'll get the best route here. All right, thank you.